Hello, everyone. Thanks for attending this talk. Today, I will talk about fractional certificate for bounded functions. This is a joint work with Shachar Lovett. Okay, let's get started. So in this talk, I will discuss three parts. First, I will recall the complexity measures of Boolean-valued functions. Then I will talk about bounded functions. In specific, we'll focus on the fractional certificate complexity and fractional block sensitivity for bounded functions. Okay, let's get started with from the first part. So complexity measures of Boolean functions. Okay, so the area of Boolean function analysis has been broadly studied in past 30 years. One of the most important questions here is that for any Boolean functions, how could we measure, how could we quantify its complexity? So in the past, in the last years, many definitions or many notions were introduced from different motivation, different application scenarios. These notions include decision tree complexity, polynomial degree sensitivity, block sensitivity, certificate complexity, and more. So all of these notions were introduced to measure the complexity of Boolean functions. Okay, so as we mentioned before, one of the important notions in today's talk is the certificate complexity. So let me first recall the definition of certificate complexity for Boolean-valued functions. So given any function f, so for every input x, the certificate complexity of f at x is the minimum size of set I, such that for any other input y, whenever y and x are identical on I, then fx is equal to y. Fx is equal to fy. So this is the certificate complexity for a specific x. So then the certificate of complexity of the whole function f is simply defined by maximum cfx, where x is chosen from the whole domain. Okay, so this is the definitions. So in the past 30 years, people made a lot of efforts to understand the relationships between these different measures. So finally, we finished all of these connections, and we know that all of these notions are polynomially related. So for example, so we can show there exists a universal constant C such that for any Boolean-valued function f, its degree is upper bounded by sensitivity to the C. So yeah. So okay, so this is the status of the Boolean-valued functions. Then how about the bounded functions? Okay, so let me first define the bounded functions. A function f is bounded if for every x, fx is between 0 and 1. So recall that in the Boolean-valued case, we require that fx is equal to either 0 or 1 for all inputs. But now we only require it to be between 0 and 1. So this is a natural generalization of Boolean-valued functions. Okay, so why should we care about the bounded functions? So at first, this is a natural generalization of Boolean-valued functions. The second, bounded functions can also be used to capture quantum queries. In the application of quantum computing, the Boolean-valued function is no longer strong enough to capture quantum queries. Instead, bounded functions are good. So this is another important motivation for us to study bounded functions. Okay, so then how could we quantify the complexity of bounded functions? Okay, so in the Boolean-valued case, we have so many notions to capture the complexity. So in the bounded function, for the bounded case, we can also look for a simple nature generalization. For example, we can define this decision tree complexity. So given any f, bounded function f, we say that a decision tree T epsilon approximates f if for random input x, the absolute value of fx minus tx is upper bounded by epsilon. Okay, so in our definition here is the approximation is in the sense of L2 norm approximation or say average case approximation. We do not require that for every x, fx minus tx is upper bounded by epsilon. So we only care about the average case. Of course, if we define the pointwise approximation, there could also be some interesting problems there. But in here we are focusing on for random input x. Okay. So there is a regard to the measurements between different notions. Okay, so we can also ask similar questions here in the bounded case. Actually, there is a very interesting conjecture asked by Arson and Ibanez. So for any epsilon parameter epsilon, so let f be a bounded degree d polynomial. So could we show there exists a decision tree T of depth and polynomial d and 1 by epsilon, that epsilon approximates f? Okay, this is a generalization of the Boolean-valued case. So basically, this question is asking what's the relationship between degree, polynomial degree, and the decision tree complexity in the bounded case. Okay, so as we mentioned, this statement is true for Boolean-valued case. And okay, so the Arson Ibanez is asking for the bounded case. Actually, there is also a strong motivation from quantum computing for this Arson Ibanez conjecture. So it captures what is the power of quantum queries. Okay. Okay, so then let's move to the notion that we're interested in. So in this talk, we are interested in a notion called fractional certificate complexity. Okay, so as I mentioned, our motivation was for the Arson Ibanez conjecture. So, but this conjecture asking connections between decision tree complexity and polynomial degree. Then why should we talk about fractional certificate complexity or certificate complexity? Okay, so let me tell you the reason. Is that, okay, let me first recall in the Boolean-valued case, how could we prove the polynomial degree and the decision tree complexity are polynomial related? So the proof is using the following framework. So we first show that the decision tree complexity is upper bounded by the square of certificate complexity. And then we show this is upper bounded by block sensitivity to the force. Finally, we show this is upper bounded by degree to the 8. So this is how should we finish the proof of makes the connection between the decision tree complexity and the degree. So that we always use certificate complexity or block sensitivity as a bridge. So as far as I know, I don't know any proof, even for the Boolean-valued case, is that I don't know any proof making connections between the decision tree complexity and the degree without using neither certificate complexity nor block sensitivity. Okay, so this is what happened in the Boolean-valued case. Okay, so then if we want to study a conjecture, I mean in the bounded case, the first idea was always to ask whether we can generalize the Boolean-valued case to prove the bounded case, right? So this is the first idea. Okay, so then we can also try to generalize the notion of a certificate complexity to the bounded function. Okay, so of course we usually have a very nature generalization here is that the epsilon certificate complexity. So for the epsilon certificate complexity of f as input x is defined as the minimum set size of a set I, such that for every y, whenever y and x are identical on I, then fx minus fy, the absolute value is upper bounded by epsilon. Okay, so we no longer require that whenever yi is equal to xi, then fx is equal to fy. We only require they are very close. Okay, so this is a general, this is intuitive generalization of the certificate complexity for Boolean-valued case. Okay, so but unfortunately, so this definition seems not a really good one. Let me give you this example. Let f be a be a function defined as follows. For any input x1 up to x2 up to xn, so we just define the output to be summation of xi's divided by n. Then, of course, this is a degree 1 bounded function. However, if we would like to study the certificate complexity of f, we can choose x to be 0, 0, 0, 0, 0, and we just choose epsilon to be 0.01. So then we can show the certificate of f at x is omega n, meaning if you choose any set of I of size little o n, then what happened is that we can find a y such that yi are all zeros. But for all of the non-ith parts, we fix all of them to be 1. So then we find a y such that y and x are identical on I, but fx is equal to 0 and fy is very close to 1. So there's a big separation. So now it tells us the certificate complexity of f is omega n. So now we see a big separation between certificate complexity and polynomial degree for bounded function. So therefore, this epsilon certificate complexity seems not a good one. Okay, so then that's the motivation, one of the motivation for studying the fractional certificate complexity. So the question is what should be a correct corresponding notion of certificate complexity in the bounded case. So now our proposal was the fractional certificate complexity. Actually, so now let me first define this epsilon fractional certificate complexity. So epsilon fractional certificate complexity of f at the input x is the minimum k such that there exists a distribution pi over n such that for every y, whenever y and x are very close under this distribution pi, then it implies fx minus fy is bounded by epsilon. So this is a generalization of this epsilon fractional epsilon certificate complexity. The generalization is that we no longer require I to be a set. Instead, we allow it to be a distribution pi. Okay, let me give you a quick lemma to demonstrate how it is a generalization of the certificate complexity. Okay, so we have this simple lemma is that for every ith and the very input x, the fractional certificate complexity is upper bounded by the certificate complexity. So the reason is the following: let I be any set such that whenever y and x are identical on I, then it implies fx minus fy is bounded by epsilon. So then we can, given this set, we can define pi to be simply to be the uniform distribution on I, and we choose k to be the set I, the size of the set I. So now we have that for every y, such that for a random x, for a random I, probability yi is not equal to xi is upper bounded by 1k, 1 divided by k, then it implies y and x are identical on I. And it also implies fx is the fx minus fy is upper bounded by epsilon. So therefore, we can easily translate a certificate set into a certificate distribution. So therefore, the fractional certificate complexity is a simple generalization of this certificate complexity. Okay. So now we can also define the epsilon fractional certificate complexity of f is to be the maximum of x fractional certificate of fc epsilon fx. So we just choose the maximum x where x is the chosen from the whole domain. So this is a simple generalization of the is a corresponding generalization of the Boolean-valued case. Okay. Okay, so then what is our main result in this paper? So in this paper, we studied the connections between the fractional certificate complexity and polynomial degree. So our main result is the following: let f be any bounded function of degree d polynomial. Then for every epsilon, then we have fractional certificate complexity of f epsilon fi fc epsilon f is upper bounded by linear of d to the 8 times log n 16 log n to the 16 divided by epsilon to the 4. So we can So we can, in fact, in the case of Aronson abundance conjecture, we can always assume that d is larger than log n. So the reason is that whenever d is much smaller than log n, we can first apply a hypercontractivity inequality to approximate the original f by just and then reduce the coordinates. Okay, so anyway, so we can always assume that d is bounded by polylog n. So therefore, this theorem tells us in this region, the fractional certificate complexity is upper bounded by polynomial in d and 1 divided by epsilon. So let's compare it to the fractional certificate complexity. On the other hand, for the let's recall the certificate complexity case. In that case, we have that there exists a degree 1 polynomial which has certificate complexity omega n. So they are huge. This is a huge separation. But on the other hand, for the fractional certificate complexity, we know they are polynomial bounded. So now our proposal is that the fractional certificate complexity might be a correct corresponding of the certificate complexity in a Boolean-valued case. So yeah, then the question is that whether we can use the fractional certificate complexity as a bridge to make the connections between degree and the polynomial polynomial degree and the degree complexity. Okay, so our proof here, we use some idea from duality of linear programming. So I probably do not have enough time to explain our proof, but it is online. So it's welcome to please read our paper if you're interested. Okay, so the last part in this talk is the fractional block sensitivity. Okay, so as we mentioned, so in the Boolean case, in the Boolean-valued case, if we would like to make connections between the tree complexity and polynomial degree, so we, at least in my knowledge, all of the proofs have either used the notion of block sensitivity or certificate complexity as a bridge. Okay, so then this block sensitivity is also a similar is also a similar notion here. So let's talk about the fractional block sensitivity. Okay, so let me first introduce the epsilon sensitive block, sensitive blocks. So the definition is the following: let f be a bounded function. So the family of sensitive blocks is just defined by all of the block set of coordinates, such that whenever if we fit all of the bits on B, then we changed the outcome of this function fx by at least epsilon. Okay, so this is also a generalization of the sensitive block in a Boolean-valued case. Okay. So then what is the fractional block sensitivity? So given any bounded function f and any input x, we define the fractional block sensitivity as the maximum value k, such that there exists a distribution nu over the block sensitivity, such that for every I in N, then the probability such that I is in B is upper bounded by 1 divided by k. So actually, so this is the fractional block sensitivity is a generalization of the block sensitivity in the Boolean-valued case. So in a similar as the fractional block sensitivity, we can also generalize any block sensitivity into the block sensitivity in the Boolean case into the fractional block sensitivity in the bounded case. In fact, we always have that block sensitivity is a lower bound of fractional block sensitivity. Okay, and similar, we can also define the epsilon fractional block sensitivity of f. It's just the maximum fractional block sensitivity of fx, where x is chosen from all of the domain. Okay, in fact, in the fractional case, there is also an very interesting thing is the fractional block sensitivity is actually equal to fractional certificate complexity. So this proof is just followed by a duality of linear programming. Okay, so as we mentioned that in the Boolean-valued case, whenever we want to make a connection between degree and decision tree, we always have to use something either fractional block sensitivity, either block sensitivity or certificate complexity. And in the bounded case and in fractional case, we show that they are actually the same. So the question is, so now an interesting question is that if we want to solve the AA conjecture, Arrowson-Bendix conjecture, could we use some ideas from fractional block sensitivity or fractional certificate complexity? Actually, so in this paper, we also showed another result about the sensitivity, sensitivity blocks. So we show that whenever f is a low degree polynomial and has a large variance, then we can always then for a large fraction of x, we can always find a small set bx, such that whenever if we flip if we just flip a few number of bits of x, then we can flip the outcount of f by at least omega epsilon. So meaning for a significant fraction of x, we can find a small sensitive blocks. So this is for every for a significant fraction of x, we can find it. Okay, so this is all today. Thanks very much.